Alright, so this video we're just actually going to do a couple examples here of resistors and series and parallel. But what we're going to do here is we're going to actually look at how we can combine these in series and in parallel, how some of these circuits you get to combine the elements here. So we're asked to basically find REQ. Now you again might want to pause the video so you can sketch the circuit out. Find REQ. Now it's not necessary to do this, but I'm just going to erase this voltage source here because basically I'm looking for what's the equivalent resistor here. Now the first thing I want to note here and kind of star this is not a purely series or parallel circuit. So if it's not purely series or parallel, what do? Well, we look for elements that are in series and elements that are in parallel and proceed how we would from there. And oftentimes you will redraw your circuit. Sometimes people don't bother, but I find that sometimes people make mistakes if they don't. Now typically what you want to do is, since REQ here is on the left hand side, I want to start on the opposite side of that. So I'm going to start all the way over here on the right hand side. And if I look here, we have to be careful here, because if I look here, well, I've got a node here, and this 3 ohm and 6 ohm are clearly in series. So the 3 ohm and 6 ohm are in series. But we know if they're in series, we could just get an REQ for them. So their equivalent resistance, it's not the REQ we're looking for, but we could look at the equivalent resistance of those two resistors. Would be 3 plus 6, which is 9 ohms. Now, while it's technically not necessary to do this, I'm going to redraw this circuit here. 4 ohm, 18 ohm. Those are my connection points. And then now we need to figure out, well, this 3 ohm and 6 ohm we combined in series. And well, let's look at here. The one branch of the 3 ohm is connected to the 18 ohm resistor, and the other branch of the 6 ohm is connected to the 18 ohm resistor. And these are the two resistors we combined in series, but now we have to make sure that we connect it up the right way. So the reds here are the dots on how we would connect it up. So we'd be connecting it up here like so. And this would be 9 ohms. But now, if I look at this circuit, and again, just kind of taking it from the rightmost spot here, I'm going to look at these two elements here, because it's still not purely resistive or parallel, but I can see that this 18 ohm and 9 ohm, the 18 ohm is in parallel with the 9 ohm. And as a side note, we didn't mention this yet, I believe, but these double lines here is just a shorthand for parallel. I mean, it comes straight from mathematics and geometry, and we will use it as far as representing things being parallel. Now, they have an equivalent resistance as well, and we could compute that several ways. I'm going to do the 2 resistor, so I'm going to do 18 times 9 over 18 plus 9. And if I do that computation, use my calculator here to help me real quickly, we get 6 ohms for the equivalent resistance there. Actually, I should put a unit on this. This is 4 ohms. And now, again, we have to think about where the connections are. Well, there's a connection at the top here and a connection at the bottom here like this. And so we would wind up having still this 4 ohm resistor. And then I would have this 6 ohm resistor. Now, sometimes people get confused at this point on knowing whether they're in series and parallel, but just follow the rules again. Well, clearly this node is connected. It's the same node. But now, is this terminal connected to this terminal? And the answer, of course, is no. There's no wire connecting those two terminals. In fact, we have an open circuit here. So these two terminals are definitely not connected. So the 4 is in series with the 6. And I can finally talk about, okay, well, what's the equivalent resistance? So Req is going to be 4 ohms plus 6 ohms, because they're in series, which is 10 ohms. Now, what that means here, I'll go back to the original problem and redraw the voltage supply in, is this voltage supply, even though there's all these other resistors, the equivalent resistance that this voltage supply is seeing is 10 ohms. So while that's interesting, that's not going to tell me, for instance, what the voltage across the 6 ohm resistor is or what the current through the 6 ohm resistor is. But it's still an interesting thing to notice that the voltage is seeing an equivalent resistance of 10 ohms. And that's going to be important later on when we talk about maximum power transfer, and also just knowing what kind of load you're connecting up to your power supply. You've probably heard of things like that before, depending on what you've done. If you haven't, that's fine, but we will talk about it in more detail. So let's look at one more example here. It's going to be a similar one. In this case here, we have a 5 amp current source. We have a 10 ohm resistor, a 6 ohm resistor, a 64 ohm resistor here, 7.2 ohm, and 30 ohm. And the problem is actually going to ask me to find V. So it's asking me, what is the voltage drop across this current supply? Now, you could write, loop equations or node equations and try and figure out what it's going to be based off of that. But there's actually an easier way to do it. We're looking at basically what's the voltage drop about this current supply. So what we're going to do is we're going to look at, well, what does this current supply see? If I can think about the equivalent resistance this current supply sees, I can then easily compute what the voltage is across that current supply. So I'm going to compute R equivalent. Now I'm not going to go in as much detail as I did here in the previous example. I'm just going to kind of draw some things and redraw circuits. Those components, again, starting from the right, it's not necessarily starting from the right, it's starting from the opposite side of the power supply. The power supply was on the right, we would start on the left. So we have 6 plus 10 ohms, so that's a 16 ohm equivalent. So again, if we're looking for equivalent resistance, the circuit would now look like this. We have 64 ohm and 16 ohm. And I'll go ahead, it's the next thing if I look at here, I have these two resistors in parallel, and I could do the two resistor formula again, but I'll go ahead and do the other formula for that. Just to show what the original formula for it is, and again to kind of emphasize that you can do this any way, you'll get the same answer. In this case we get 16. That can't be right, I did something wrong here. Just a second. That looks better. 12.8. And then redrawing the circuit. And you'll see I redraw the circuit a lot. Now, when you get comfortable with this, you might not have to redraw the circuit as much as I'm doing here, but until you get comfortable with this, in my opinion, makes sure that we don't make a silly mistake. All right, so then again, the next things that I'd be looking at is I've got this 7.2 in series now with the 12.8. So the 7.2 plus 12.8 clearly gives me 20 ohms. And then finally, I have making sure to connect the nodes up correctly. 30 ohm. 20 ohm. And those are in parallel. So my REQ now, I'm finally ready to find REQ, is equal to, well, I'll do the 2 resistor formula, 20 times 30 over 20 plus 30. And we get 12 ohms as the equivalent resistance. Now, let's go back to the original circuit here. I have a 5 amp power supply, and I found this red arrow R equivalent. So if I were to redraw the circuit now, I still have this 5 amp power supply, and I've got plus minus this voltage, which is what I'm looking for. And then I have a 12 ohm resistor. But let's think about this for a second. These nodes here, these two components, are in parallel, so they have the same voltage. The other thing we can clearly see is that if I look at the current here, well, there's only one way that the current has a path to go. You know, if I draw what the current is doing, it can only do this here, right? There's no other nodes or branches that it can go off into. So we also know that the current through the 12 ohm resistor is 5 amps. And so the voltage through the 5 ohm resistor is simply 5 amps times 12 ohms, which is 60 volts. But since V and this V5 are in parallel, we know that the voltage that we're looking for is 60 volts. So yeah, I still had to do some resistors in combination, but if I tried to use KCL or KVL to find this, I'd wind up with a system of equations and a system of unknowns that I'd have to solve in order to figure out what this voltage was. Whereas this approach, we just combined resistors in parallel and series, which isn't too bad, and we're able to get what the final voltage was. I encourage you to do both of these examples again on your own without the video to make sure you understand how to do them, as well as I encourage you to do the examples that are in your text, the try these, pretty much you should always look at the example problems in your textbook, and they almost always have, like, they call them, well, some of them will call them try these problems or assessment problems or whatever they call them. They're in the text, and the reason I like those is they usually have the answers for the problem right there, so you can see if you're doing the problem correctly.